Welcome everyone to this session. Now, let me today talk about one of the most important concept, which is basis, the concept of basis in a topological space. So you might, I think you might know the concept of basis for a vector space, right? So I'm not writing it, just listen me carefully. So if you have a vector space V over some field F, the Zorn's lemma ensures that there would be a basis for this vector space. And what was basis there in vector spaces? It was a linearly independent set which spans your space, right? The two conditions were there. It's a spanning set and it's a linearly independent set, right? But why we call it basis? What kind of base it provide to my vector space? So you might have studied this that every point in that vector space, if you know the basis, you can represent every point by a linear combination, right? So equivalently, studying the vector space is equivalent to studying basis of that vector space, right? So similar kind of concept we are gonna define in topology. So I already have motivated you guys for this concept, but let me again motivate you with a sort of similar example. So let us consider a situation. So let x is equals to R2. What is R2? Real line cross, sorry, R cross R, real numbers cross real numbers. Set of real numbers cross real, a set of real numbers. So precisely the point x comma y such that x comma y belongs to R. I mean this you know. And tau be a topology on x such that. So I have a topology on x. Let me tell you few things about this topology. So such that this set x comma y such that y is equals to x plus c. This belongs to tau for every c in R, and as well as all points x comma y such that y is what? Say minus x plus c. These kind of sets also belong to my topology. Means they are open sets. They are, these sets are open. In which topology? This topology, tau on R2. You may stop the video and think about what are these open sets. So basically these are all, basically in other words, tau is a topology on R2 in which all lines with slope, you know what is slope of a line. I'm not gonna define it here. You can see if you don't remember it in I think your 12th no 10th class Cartesian geometry chapter of NCERT. If you are an Indian student or if you follow the international boards, Cambridge or some different, then you might have studied this in any standard from 8th to 10th class. So let us have, in which all lines with slope what? Plus 1 or minus 1. are open. So it's a topology in which these things are open. Fine. Now, let me tell you something. Let us take some point. Let A comma B, let A comma B belongs to, say, R2. So let me have a picture. So say this is your R2. Let us say you have A comma B here. Okay. Now, let us see this line. And let us have this another line like this. Let me tell you what I am doing. So I am taking two lines passing through A comma B with slope +1 and -1. Now you may wonder, is it possible? So the answer is yes, this is possible. Let me tell you why. So, uh, okay. So let us have L1. Okay, let us see if you have something like this, equation like this, y is equals to x plus c. And let us say A comma B satisfies this equation. So B is equals to A plus C. So this implies C is equals to B minus A. So L1, define L1 as all points in R2, okay, such that y is equals to x plus b minus a. Okay, guys. So what is this? This is your red line in this picture. And similarly, L2, define all x comma y in R2 such that, so let us have this kind of line, say minus x plus c, and if a comma b satisfies this, so c should be b plus a. So y is equals to minus x plus b plus a. So this is precisely your blue line in this picture, okay, in this above picture, right? What you have, guys? L1 intersection L2. What it is? Singleton A comma B, guys. No? And L1, L2 belongs to tau. This implies L1 intersection L2 should be where? In tau. Why? Tau is a topology, right? But from the definition of topology, we have this thing. So what you get here? You get is A comma B. This singleton is open in this R2 along with tau, right? For every A comma B in X or R2. I have taken my set X to be R2. I think this is fine. So from here, since any union of open set is open. So what you will get? What you will get, guys? That this implies this tau is nothing but it is 2 to the power x. It's a discrete topology. What kind of topology we have? Discrete topology. So what is the lesson here? Let me tell you. So what is the observation is observation. In a topological space, there might be, there might be a subcollection, a subcollection of open set or sets which describe the whole topology, right? The whole topology. That is what is the observation. And precisely like for upcoming, I think maybe 5, 6 lectures, we would be interested in these kind of sets, these kind of sub-collections, right? So something, it's a little thing, but it describes the whole space. So what you mean in other words, you see, it is analogous to a basis of linear algebra vector spaces. A few members will tell you about every member of that vector space, right? So it is something similar to that. So let us now, with this motivation, let me finally define you guys what do we mean by a basis of a topological space. Definition. Basis of, let me write this off, in very bold thing, or maybe let's use another color of a topological space. Where is the purple one? Yeah. I will warn you not to misuse English. It's off here, not for. For and off are two different English words. This distinction you will never forget in your life from today, from few lectures onward. So what I am defining you is basis of a topological space. Okay. So you have to start with a topological space. So let X tau be a topological space. Okay. A subcollection. Say script B, you can use the LaTeX command slash math bb capital B. So you will get this letter, which I am making very badly. Or BB you can use, and some people also write in this fashion math cal. So these kind of, so basically script B, something stylish B, that sort of. Okay. So a subcollection, this B contained in, where tau is a basis of x with respect to tau, or in other words, you can just write like this. This is a better way, basis of the topology tau, or for x tau, the topological space x tau, if, what is the definition? Let us see it properly. If for any, u belongs to tau. So basically, for any open set u in tau, what you can do is, what you can do is, you can express this u as union of the members of tau. Okay, so for any u in tau, u can be expressed as union of members of what? Script B. So any set in tau you can express as member of script B. In mathematical language, if you want to write, so in other words, or there exists a subset, say this contained in script B, such that, note that, of course, this subset depends upon your set. Okay, so let me write tau u such that u can be written as, say, union B, okay, B in script, this subset, treat it as a script also. We have done these things, okay? So basically, a subcollection of topology is a basis for, sorry, of that topology if, what if you can express every open set as a member of union of that subsets, as some members of union of that subset. I hope this is clear. If it is not clear, we will be seeing examples. So be little bit, have some patience. Okay, let me tell you a simple property or a simple characterization for this concept of basis. So let us have a theorem. We will see examples. Or if you want to see now, I can also do that. So, okay, let us have one example. So, example. Okay, so let me have this. So, let us consider real line R. Okay, let us consider real line R. And let us have this B1 to be, say, open intervals. Okay, so what is B1, guys? B1 is collection of all open intervals. So what is our claim is claim B1 is a B1 is a basis for real line R, or basis of topology on real line R. Okay, that's what I said. For and off, you should be very careful. We will be seeing some another kind of distinction between these things. So it's better. Let us write here also off for now. And here also off. So these are the two same thing, like off topological space or off topology. So you can use any language, there is no harm. So the concept is, of course, associated with the open set. So of course, associated with the topology on the given set X. So there is no harm in both of these language. So Let us see why this is true. Okay, so let U contained in R be open. Guys, what it means, this is a metric space with your usual distance, right? Real line R. So this implies for any x in U, there exists R suffix x bigger than 0 such that what happens, guys? You know that how we defined open set in a metric space, right? So x minus Rx, comma, what guys? X plus Rx, right? So this is sitting inside U. Now what you do? You take the union of all such x. So this is happening for every x, right? X in U. This would be sitting inside all these kind of intervals, right? Open intervals, union of all these. So X in U. Of course, you are taking union of U any times, as many as times you want. It would be U only, right? And what is this, guys? This is also U. So what you have? U is equals to union X in U, X minus Rx, X plus Rx. And note that X minus Rx, comma, X plus Rx, where it belongs, guys? It belongs to B1 for every X in. So what you have? Any open set you can express as members of B1, right? Any open set you can express as member of B1. So what it means, guys? It means B1 is a basis of topology of real line R, of topology on real line R. So B1 is a basis for, of. I can use actually for here, but I want you to learn some different concept. That's why I'm very precise here. So let us have of real line. Whenever I'm saying of topological space X tau, I means of topology tau. Like I said, you both languages are same. Don't get confused with this thing. Because what is topology? Topology is associated with topological space. Topological space is associated with the topology, right? Or topology. So that's what it is, right? So okay, what I have written here, if you see, uh, not the. It means there can be more. So this is your homework, sort of. Okay. So let me give you an exercise. Show that. Let us have like, yeah, show that B2, so A comma B, such that in, of course, an open interval in R, so that A comma B belongs to rational numbers is also a basis of topology on real line R. You know what is real line R. We have used it many times, right? So I hope you can do this. This is your homework. And see, this is a, very important example. This kind of thing we will encounter again. So this is about the definition and the example. So let me proceed further. I want to give you, one sort of characterization of a basis, an equivalent definition in other words. So theorem. Let X tau be a topological space. B is a basis for, oh sorry, X tau if and only if for every open set. So let us see carefully. If and only if, what is the equivalence statement? For every U in tau and X in U. So every open set and for every point in U, what is the claim? There exists B. So it depends upon the both things, the point and the set. So X, U in script B, such that I think you may guess it. It's like something like interior point. So something like that. So analogous to that. X belongs to what? This B x comma U. Why I'm writing x comma U in suffix? Just to show the dependency on the point and the set U is contained in. So this is what, you know, your result is. So let us see how we can prove this. So, okay, let us proceed in forward direction. So let B is a basis. Okay, and let U belongs to tau. What it means, guys? This implies there exists some subset of script B such that U can be expressed as union, right, of its member. Very nice. I hope this is clear. This is just by the definition of basis. Right? Now, for any x in U, this implies x belongs to this union now, right? So what it implies, there exists some, of course, these B depends upon U and then point. So I can write like this, U comma X or X comma U, whatever you want to write. There will be some member, right? Such that, and this is, see, this is inside script B, such that X belongs to BXU, and this is precisely in U, right? Where is BXU? Guys, this is in finally basis only, B only, right? That's what we wanted, right? I think this is obvious, more or less. So we are done. Now the converse part is also, it's also similar. So let us assume this. So let us assume let script be contained in tau such that for every, so this script B is in tau, okay? So for every what open set U in tau and X in U, what we have? There exists B X comma U in script B such that what will happen, guys? This X should be inside B X suffix U, which is inside U. Now the same logic as above. This is happening for every U, for every X in U. So what you can do is you can take these kind of unions here. You see, that's why I have written suffix XU. It matters. So now you can vary your X. So sometimes using the precise notations is a useful thing. What is this, guys? U only, right? So what you have? U is union BXU, X in U. Where were these BXU? These were in script B, right? So this implies script B is a basis of tau on X. Why? Because, right, that is what the definition is. So you see, uh, I hope this is clear, right? Okay. So you see, this is the concept of basis in a topological space is somewhat similar to the concept of, basis in a vector space. In a vector space, bases help you to identify the every member of the vector space. And in a topological space, basis helps you to know about every member of topology, right? So it is analogous to that. So we will end this lecture by say one more example. There can be many, but I wanted to give you one more example. One more very, common example. That's what I wanted to give you. Let XD be a metric space and tau XD be corresponding topology. I mean the topology induced by this metric D. Basically the collection of all open sets in metric space. Okay, guys. So what is our claim is? Claim the script B, if you take sets like this, the open ball centered at X with radius R. Where is this X? This X is in capital X and this what R. So this R is say bigger than 0. Okay. R in R, which is bigger than 0. So these kind of open balls, so basically collection of all open balls is a basis, okay, of tau dx. I hope you are very clear with this proof, right? If you still want, I will just give you a hint. For any u in tau dx, u is nothing but it can be written as like this: union x in u, okay, b x comma r x, for rx bigger than 0, for some rx bigger than 0. Okay, guys, this is hint for you. Please complete the argument. Now, see what you can do. You can maybe you can use this theorem. Where it is? This theorem. Or you can just directly apply definition, because the characterization is very close to the definition. So it doesn't matter, whatever you want to do, you can do. Okay. So this is the hint. Basically, I haven't just given you hint, I have written indirectly everything. What I want you guys to do is to properly, you know, um, write the arguments. That is very important. I have done it for you in above examples. That's how properly you have to, write the arguments. Let me have a concluding remark. In upcoming session, we will study a concept called basis let me use different color for a topology on given set X. Let me clear you here. So in today's session, we had a topological space, right? We define when this script B, which was contained in tau, will be a basis of X term, right? So in next session, what we are gonna do is given a set and some special, some special collection of some subsets of X, say script B, we will define a topology on X, say tau, such that script B will be a basis of tau. Okay, so you see, if you can relate it with one concept, you may relate it with one concept which I have given you was the concept of if you see neighborhoods. What I had done there, I had a set and a topology on it. I defined you the concept of neighborhoods and I defined you the collection of neighborhoods with we have observed few properties. Then I have taken some arbitrary set with subcollections with those properties and produced you a topology in which those subcollections will be precisely the collection of all neighborhoods. So the neighborhood one lecture you can revisit. So this is also, a similar kind of concept. And after this session, you are free to use whatever you want to use basis for this topology, for our topology, of this topology, of some topology. You see, when I'm using for and of, I'm changing the second word just next to it. So carefully, you would be able to do these kind of things. Let me stop this session here only. Thank you very much.